Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very delighted to have Kostas coming over all the way from MIT. These kinds of things are known to happen. People do actually manage to move back and forth. Kostas has done it in real life. Was a postdoc here spent a year as a postdoc over here before he schlepped all the way over. And today he's going to tell us about Myerson auctions.
Yeah, so I'm glad to be back. Let me turn on my mic. Actually, we exchanged posts with Madhu, so I left and he came. So. I don't know. So I'm going to talk about optimal mechanism design in multidimensional settings. I'm going to explain what this means. And it's joint work with my students Yang Kai and Matt Weinberg at MIT. So I don't really need to introduce auctions here in this audience, but let me do it anyways, fast. So auctions are pervasive in our online experience. So in online marketplaces, when we search the web, or when we read the New York Times, okay? So the mathematical abstraction that I'm going to use today is that we have an auctioneer that has n items to sell, and we have m interested parties and bidders, each of whom have a value, usually secret, Vij, about the items. And then the auctioneer's goal is to design the auction, so announce the auction to the bidders. Then he's going to elicit bids from the bidders on the items or bundles of items. And he's going to implement the allocation and pricing rule that he has specified. On the other side, the bidders, and I might have some problems with PowerPoint today because it's been truncated there. So its bidder uses as input the auction specification, her own values for the items, and her beliefs about the values of the items to the other bidders, and then submits their bids, and their goal. Okay, cool. So I'll just keep going. So the goal of its bidder is to optimize your own utility. Okay, so the rational, selfish people who want to optimize their own utility. The goal of the auctioneer is to optimize her revenue. And I'm not going to talk about social welfare today.
And is it all private values?
The VIJs?
Yes.
Yes, I'm going to talk about what I assume. Yes. So, and the bidders may have budget or capacity constraints. So just to go a bit forward, so I'm going to assume that the budget and capacity constraints are public. I'm going to have Bayesian information about the VIJs, and I'm going to specify exactly the model in a few slides. My model for the bidders is that they have additive valuation over bundles. There is neutral, and they have quasi-linear utilities up to their budget. So what I mean by that is that, what I mean by additivity is that the value of a bundle to a bidder is just the sum of the contents up to the capacity. Okay, so if I'm given a bundle of at most my capacity, I'm just summing up the values. Otherwise, I'm just going to pick the top CI items in my bundle. By quasi-linearity, so all of this is standard. I'm just going to go through it quickly. So quasi-linearity is that the utility derived by a bundle is the value of the bundle minus the price I have to pay, or infinity if the price exceeds my budget. And again, this and that, the budget and the capacity are public knowledge.
So that's the definition of quasi-linearity?
No, quasi-linearity is just this, the assumption that my utility is just values minus price rather than some other combining function of value and price. And right, so and additivity is this, right? And I'm superposing capacities and budgets here.
So
yeah.
Is
capacity constraints is from the user side, right? Like, yes, you can possess like CI items.
Yes, so the user is
standard assumption, you say?
I mean, many people work with unit demand, so it's like I want a certain number of items, and I have certain budget. So many people have focused on unit demand bidders. I'm extending that to people who want more. And risk unitarity I'm fine with taking expectations. I don't care about risk, variance, or whatever. My mechanisms, because of the revelation principle, are going to be direct revelation, and I'm going to make them be either incentive compatible or Bayesian incentive compatible.
So you're going to tell us what those words mean?
I will, yeah. They both mean truthful, that I'm going to truthfully reveal my values for the items. So the mechanism has to make sure that people have the right incentives to truthfully report. And the difference between this and that is what information I'm using to reach the conclusion that bidding truthfully is a right strategy. And I'm going to give the precise definition later. So coming back to my model, so the auctioneer wants to optimize his revenue. What would happen if he knew the VIJs exactly? All right, so that's an algorithmic problem. There's no incentives. The auctioneer knows everything. And if the bidders were unit demand with no budgets, then what he can do is just compute a max weight matching to match the items to the bidders. Then he can define a really stringent type of auction that is going to basically implement the matching and extract exactly the whole surplus. Okay, so it's going to be very stringent, tailored to the matching, okay? Getting all the surplus. And you may ask me what will happen if the bidders are not in demand or have budgets or whatever. And I'm going to claim that this is fine if I resort to randomized allocation rules. So I can implement randomized allocation and pricing rules that can deal with extracting the full surplus, in this case too, as long as I know perfectly the values of the bidders for the items. All right? So obviously, that's a bad assumption. One in algorithms would ask what happens if the auctioneer has no idea about the values. Okay, so in a worst case sense. Okay, that's what we do in algorithms. Suppose the auctioneer has no idea what the values are. How would he go about optimizing his revenue? And what I want to say is that then all the bets are off as far as algorithms are concerned, and extracting the full surplus is concerned. So, and the example, I mean, I'm not going to prove it formally, but I'm just going to show a picture that is going to convince you about that. So suppose that my true bidders are these guys, and this is not to scale, right? So there should be a pixel in this picture, all right? So, suppose these are the true bidders, but they're bidding for the single painting through their agents. So now the auctioneer is going to announce some design. No matter what the rules of the auction are, there's no reason why these guys are they're gonna pay as much as they could possibly pay. In particular, I mean, this auctioneer is in a good situation because he's probably gonna extract a factor of 40 of the optimal surplus or something. But if I replace Layton with another Daskalakis, then so the factor is going to be terrible. Okay, so I'm not going to prove it formally, but in general, under worst case assumptions, there's no way I can guarantee any constant factor of the surplus that exists in the market. So this is well known. Everything so far is well known. So let me go. Sorry,
will you prove it that you can get a constant factor, or is it well known that you can get a constant?
It is well known and should take you 5 minutes to
Proof by picture.
Yeah.
No, but I don't understand something like Okay, yeah, let's move on.
I mean, unless this guy has beliefs about how this painting is worth
okay, sure, okay. Okay, I thought that there
he has no idea what the bidders are willing to pay, what the values are for this.
Sure.
Okay, so there's.
I thought there is some underlying. Okay, that's true.
I have no idea, so I cannot get the best I could get, right? So, and computer scientists would resolve this issue by looking at the competitive analysis frameworks and trying to argue that, well, I don't know, but I can get a constant factor of some benchmark. And really the trouble is that about finding the right benchmark, and social welfare is not the right benchmark. So if you're what I tried to argue before by picture is that if your benchmark is the social welfare, which is the obvious benchmark, you cannot hope to get any constant factor. No algorithm, no online algorithm for allocating the items to the guys, to the bidders, is going to get any constant factor of the social welfare. All right? So finding benchmarks that are useful and actually say something about the optimality of your mechanism is an interesting direction, and I'm not going to talk about it either today. Okay? So what I'm going to talk about is when I have Bayesian information about the bidders' values for the items. So I'm going to assume that the values, so V denotes everybody's values for all the items. Okay, so that's a n times m dimensional vector, and it comes from some distribution that is known to the auctioneer and to all the bidders. Okay, that's my model today.
So it's some one huge joint distribution.
It's a huge joint distribution, and this is the problem I'm going to look at. Okay, so suppose the auctioneer and everybody has a prior distribution about where these values are sampled from. Okay, so this is what is called optimal mechanism design. All right, so that's the definition of my problem. And from now on, I'm going to get into the real part of the talk, okay? All right, so recall I have m bidders, n items. The values are drawn from a joint distribution that is known. Bidders have additive utilities up to some capacity. They are risk neutral, and they're quasi-linear and up to their budget. All right? Okay. So what's the history of the problem? So we know everything about selling a single item to many bidders, and that goes back to Myerson. The statement of his theorem is from 81 is that there is a single, if there is a single item for sale and the bidder's values for that item are independent and they come from known distributions, there is a closed form revenue optimal auction. In fact, Myerson's design is not restricted to just selling a single item, but can be generalized to what is called single dimensional domains. I'm not going to formally define what this means. I'm sure some of you know already. But let me just explain what I mean by closed form. It's really that revenue optimization in this Bayesian problem reduces to just computing a max weight matching of a related problem. Okay, that's what's closed form about it. It does not necessarily mean that in all settings going to be efficient. Okay, but it means that I can take my description, the description of the problem with the distribution for the values, and I can create a different problem where all I need to do is to compute a max weight matching. Okay. So, and as an example, let me just give the i.i.d. case of Myerson's auction. So, right, so suppose every bidder is sampling a value from the same known distribution, so they're i.i.d. bidders. Then what the design is the following, of the optimal auction is the following. So the auctioneer is going to looks as follows. The auctioneer is going to do some pre-processing. So he's going to start with the value distribution, that the big joint distribution, in this case a product distribution. So just look at the marginal of every bidder. He's going to do some operation called ironing. I'm not going to get into that. He's going to use the iron distribution to compute some reserve price, and then he's going to set up a an auction as follows. So he's going to elicit bids for the item from the bidders, so B1 through Bm. And he's going to introduce a virtual bidder who's going to bid the reserve price. And all he's going to do is he's going to give the item to the highest bidder or virtual bidder, and he's going to charge him the second highest bid or reserve. All right? So this is the optimal auction.
And R is announced and fixed,
R is announced and fixed.
independent of what
They bid.
So the bidders know it. when
They know the reserve.
Okay.
So what is that auction? What does it remind you? It was on my first slide. It's essentially implementing what eBay does. Okay, so there is some reserve and people can bid, and the outcome of the eBay auction and this auction are the same. Okay, and the revenue. Assuming that whoever is selling the item uses the right reserve, right, and not some heuristic one. All right, so that's what we know. And this design can generalize to non-i.i.d. bidders. It's more complicated. It's not as intuitive as this, and I'm not going to present it here. But I'm going to the case of many items. So a central open problem after Myerson is, are there computationally efficient revenue optimal auctions for selling many bidders to many items to many bidders? All right. So there's been a large body of work, and you can look at this paper if you want, the survey paper by Vincent Manelli in economics. And there are results for restricted settings, but not for this general model I described. And on the CS community side, there are constant factor approximations. These are a couple of references for that. But the factors that they get are bad, and really we don't know of any auction that achieves this optimal revenue. For instance,
This is still the Bayesian setting. Right?
still, yeah. So it's the Bayesian setting, and So, and I mean, just as an example challenge question is selling two items to many bidders, and supposing that all these edges in this graph are i.i.d. from the same known distribution. Okay, so it's just doing the eBay auction with one more item, and assuming everything is i.i.d.
And each person has a capacity of one?
Even that, yeah. Say every person. Let's just leave it at 2 to avoid some trivialities. Okay, so actually 1, yeah. So 1 is probably harder. So suppose all these values are i.i.d. from D. What is the generalization of the eBay auction to this setting?
Is it like a combinatorial auction that like someone wants to just get one of them but not both, or something like so?
It's linear in the price. I mean, you want to get
but there's utility.
the values are linear, right?
Okay.
Yeah. All right. So what's the generalization of the eBay auction to this setting, for instance? Okay. So we can solve this case and some bigger class of problems. So here's our main result with Matt Weinberg. So there is an efficiently computable, nearly optimal revenue auction when either the number of bidders or the number of items is an absolute constant, and the other side can scale. And more precisely, the settings we can deal with are the following. So for the constant number of items case, we allow the values of each bidder for the items to be arbitrarily correlated. Okay, but we assume that the bidders are i.i.d. They come from the same distribution. So we have a constant number of items. We have many bidders. Every bidder has an arbitrarily correlated joint distribution on the items, but the bidders are i.i.d. They're sampled from the same distribution.
So just to understand, if it went for the efficiently computable aspect, all this is known, or is it also not known? Computability.
So I can, in some cases, and I'm going to show that, I can set up a giant LP that finds the optimal auction.
So it's the efficiency that's
the
focus.
efficiency, yes.
Okay.
I mean, there are some issues also for. I can set up an infinite size LP in general where that finds the optimal auction. Okay.
Without any assumption.
For the model I described, yes. For any joint distribution, additive bidders with budgets and capacities. And so for the constant number of bidders, we require each bidder to have i.i.d. values for the items, but bidders can have different distributions. So this may be hard to parse, so let me give you the picture. So our constant number of items result is I have a constant number of items, say 3, many bidders. Every bidder has an arbitrary correlated joint distribution on his values for the items, but I assume that the bidders are using the same distribution, that they come from the same population. Okay. The constant number of bidders result is I have 3 bidders, constant number of bidders, and many items, and now all these edges are i.i.d., but bidders can use different distributions. Okay, so that's pictorially the result. Yes.
Is the distribution here, or are the values here always continuous? So you're not using discrete values anymore?
Yeah, that's a good question, and I'm going to say
the
exactly.
LP comment you made?
Yeah, so the LP comment fails for continuous distributions, for instance, or infinite support distributions.
That it was known in the literature how to write down that LP?
I'm not sure if it's known, but it's fairly obvious to me. So I don't know. So, it's immediate. Maybe Rakesh, I don't know.
Yeah, it's immediate, right? Because you just have incentive compatibility and feasibility.
I'm gonna show the LP in a few slides. So
it's infinite. So that
it's
it's infinite means that it's not discretized, doesn't cause many problem. Is that what you mean?
discretizing has problems.
Right.
So that's why I'm not going to discretize, and I'm going to have an infinite LP that has some variables for every point in the support.
Okay, fine.
So let me qualify a little bit the result. So notes. So I can do arbitrary budget demand constraints, and I explicitly price bundles. My solution concept is either Bayesian incentive compatibility, so that's exact, no epsilons, or epsilon incentive compatibility. So for incentive compatibility, I have some problems with discretization, and I can only show epsilon incentive compatible results. While for Bayesian incentive compatibility, I'm exact. And nearly optimal means that I can do optimum revenue minus epsilon for any desired epsilon if my distributions are line 0, 1. Okay, that's really the only case where a narrative approximation result makes sense. Or I can do a factor of 1 minus epsilon of the optimum if my distributions are monotone hazard rate. I'm not going to define what monotone hazard rate is, but exponential, normal, uniform are in this class. It's a common class of distributions used. Okay, so if you can take your continuous distribution over a bigger potential support and shrink it and normalize, this is finite support. You normalize to 0, 1, I'll get you opt minus epsilon. If you don't want to do that and you have infinite distributions and so on and so forth, I'm just going to give you a factor of 1 minus epsilon, assuming that the distribution is monotone hazard rate.
So can you just tell us what does it mean to have an efficiently computable mechanism? Which so it means that given everybody's bids,
I have to specify an allocation rule and a price vector.
And all of this is efficiently computable, and because it's incentive compatible, everybody will just tell me the values, and there's no. Okay.
I mean, in principle, that raises an interesting point. So, in principle, there's no reason to expect that there is a succinct description of a mechanism in this scenario. Because, for instance, if every item may have, every marginal on every item has support 2, then there is exponentially many. There is like 2 to the n times m possible profiles of bidders. So if I just had a list, if all I had to do is to output a list of 2 to the n times m, allocation rules and price vectors for each of these possible bid vectors, then I would be dead. So, and in principle, there's no reason to expect that there is a succinct description of a mechanism in this scenario. Okay, and that's also a problem with Myerson setting. All right, so Myerson it's an amazing coincidence that A, there is a success description of the type I showed, and that is deterministic, and I don't know, it's an amazing coincidence to me that there is such a simple solution in Myerson setting. All right, so okay, so a glimpse of the techniques. So right, so optimal mechanism design is just an LP, but it's a giant LP, and I'm going to explain how to set up this LP. So just in words first. So let D be the joint distribution of all bidders' values for all items. So it's supported in R and M, and specifies all the VIJs. So now, for every point in the support of the distribution, and potentially outside, I guess, we need to determine what the mechanism is going to do, okay? And that, what the mechanism is going to do is basically a potentially randomized allocation rule and a price vector. So I can create variables for all of that, and I can set up an LP to compute the mechanism. I'm going to show how to do that. And the trouble, the immediate trouble is that this LP is going to live in support of the distribution times number of allocations of items to bidders space, the dimensions. All right? And they're both exponential. Or even uncountable if we are in continuous distributions. Right? But even if the support is finite, the margin is finite still. If every marginal is 2 and I have exponentially many profiles, I'm dead, right? So an easy trick one can do comes from the Birkhoff von Neumann theorem that says that instead of so an allocation rule is just a distribution over deterministic allocation rules. So, and the point of this theorem is that I don't need to look for distributions over allocations. I can just project into the marginals of, with what probability every item goes to every bidder. And if I compute those, if I work with just marginals, I can, and I get back the solution from the LP, I can pull out a distribution over allocation. So I can, in principle, what I want to say is that this guy is not very problematic. So I can really reduce the dimensions to support times some polynomials. Right? And so m times.
So rather than saying how much you're what is the probability with which you allocate to each person, you're just saying which one of these bidders is going to get.
Instead of saying that with probability 30%, I'm going to give item 1 to this guy, item 2 to this guy, and then with probability 20%, I'm going to do this matching. So every allocation is a matching of items to bidders, and in principle, I have to specify a distribution over matchings. Okay? Instead of specifying a distribution over matchings, I'm going to only compute marginals of, in this joint distribution over matchings that are defined, what's the marginal of me allocating item I to j to bidder I? I can set up the LP only on those variables. I'm going to show how to set it up. Okay, so here's the linear program. So for every bidder and every item and every vector in the support of the value distribution, I'll have these variables. Okay, so phi ijv is the probability by which I give item j to bidder I if the bids are v. And PIV is the price that I'm going to charge bidder I if the bids they report are v. Okay, so these are my variables. And here's how I'm going to implement all my constraints and the incentive compatibility. So feasibility. So I want that every item is not given more than once. Okay, so an expectation. So if a sum over I, over bidders, the probability by which j is given to I should get at most 1. I don't want to give people more than their capacity. So if I find the expected number of items I give to bidder I, that shouldn't exceed his capacity. And the price I'm going to charge them should not exceed their budget. So I'm satisfying all my capacity budget constraints. Now the truthfulness constraints. All right, so let's see if I can also write the truthfulness constraints as linear functions of my variables. So what I want is that no bidder has incentive to misreport his own value vector. Okay, so this is a value vector for bidder I. Okay, so suppose bidder I has value vector vi, and he's thinking of misreporting vi and reporting vi prime instead. I want him to lose. All right, so what happens if he reports truthfully? He's going to get, remember, so phi j is the probability by which he gets item j, so his expected value is the sum of all items, his value for item j, times the probability he gets it. And then what he's going to pay is the price for that value vector. If he instead reports vi prime, he's going to get the items with different probabilities, because the bids changed now. All right, so this is what happened. And his price is going to be different. All right, so I want him to not have incentive to switch. That's incentive compatibility. After knowing everybody else's bids, I don't want him to have incentive to misreport his value. So Bayesian incentive compatibility is in expectation over the other people's bids. I don't want him to misreport. Good. This is how the two things are related. So this expectation symbol is taking an expectation over everybody else's values, assuming the bid truthfully. So this is the LP, right? And the trouble with the LP is that it needs variables for every point in the support of the value distribution. So that's going to be exponential or infinite. And the deviations, the deviation vectors can also be exponential if there are many items. Okay, so every item has support 2. There's exponentially many possible lies that I can say. Yeah.
So in setting up this LP, you've also replaced the feasibility constraints with these expected feasibility constraints. Isn't that a separate step later showing that the expected feasibility constraints are satisfied?
You can
actually
yes.
implement the way
that comes from the Baker von Neumann. Yeah.
And so the additivity valuation model is working really nicely with the marginals.
Yeah.
Have you thought about whether there's a way to allow maybe some kind of still factored valuation model and then generalize the marginal representation?
I haven't thought beyond additivity. In principle,
that's essentially why you've assumed additivity here, so you could.
Yes, I can write linear constraints here for my value.
So
yeah.
could one generalize the Bilkov von Neumann idea and build out extra factors and have marginals over?
I wouldn't be surprised. Yeah, so maybe economists, I'm sure, are more familiar with the Baker von Neumann than me.
This general paper by Kudish and Hilgren.
No, it's just Birkhoff and Bohr. It's just total unimodularity again.
How did I know you could say that?
But this is a really cool theorem, by the way, the Baker von
Yeah.
Neumann. It's surprising that you can do that. All right, so how are we going to reduce this LP? And are we going to get any structural understanding of the auction anyways? Because in principle, there is no reason to expect that this LP, the solution to this LP, which is the optimal auction, has a succinct solution. So there are two questions. One is algorithmic. Is there a way to find a solution to this LP faster than the trivial way? Is there a way to describe the solution of the LP succinctly? And are we going to get any structural understanding of the auction after we do that? All right. So I'm gonna show you what we do. It's several steps. The first step is understanding the symmetries in the value distribution and how these affect the optimality. So if you recall, the settings that are presented either for constant number of items or for constant number of bidders have some symmetry. Okay, they're either item symmetric or bidder symmetric. So what I want to understand is how this symmetry helps towards having a succinct auction. Right, here is a theorem we show. So let D be the joint distribution over every value that's supported in the set. Now let S is a subgroup of permutations. It's a subset of the full set of permutations on the items and the full set of permutations on the bidders. All right, so suppose S be a subgroup of permutations with the property that if I pick any permutation from that set and apply it to the value distribution, this guy is distributed in the same way as the other guy. Okay, so the value distribution is invariant under applying the symmetries in the set S. So suppose I have a value distribution D that has a subgroup of symmetries S. All right, so I want to see what that gives me. So what we show is that there is an optimal randomized mechanism that also respects the same symmetries in the following sense that if I plug in a permutation of a bit vector to my mechanism, the way the mechanism is going to behave is as if I had plugged in the unpermuted vector and just permuted the result. Okay, so what we show is that if you have a subgroup of symmetries in your distribution, then you get back the same symmetries in your mechanism. All right? And just like just a cultural sort of thing. So that shows where I come from. So Nash showed a similar symmetry result that's very interesting, that if a game has some set of symmetries, then there is an Nash equilibrium that simultaneously respects all these symmetries. Okay, so that's just a parallel. Okay.
Just to make sure I understand, Sn times Sm. So this is the script S itself is not a product set.
Yeah.
So the permutations may jointly be permuting the bids and the items.
Right. So the permutations
the bidders and the items.
The permutations that I'm looking at are right. So so you have this matrix, right? You permute the rows and then you permute the columns.
So for instance, the ith person might like the ith bid item more than anything else, and somehow you consider these permutations which will.
I'm not gonna put the matrix, the Vij, in a vector and consider all permutations of this vector, right? So I want permutations that permute the items and they permute the bidders. I don't want to put them in the same bag and do whatever permutations. That's not going to work. So.
Right, but the set S does not have to be only permutations that permute items, the bidders separately and the items separately. And it's not a product set.
It has to. No, it is. That's what I mean. Yeah. That's what I mean.
It has to be a product set. So
yeah, I cannot just put the Vij's in a vector and consider any subgroup of permutations of n times m.
No, sure. Okay, so maybe. All right.
So yeah, so just to make it clear, I consider sets S that have a bunch of ways of permuting items. Oh, that's what it. Right. Okay. It's not a product distribution, right? But it is right. Okay. So you're right. There is an intermediate place. So it's not a product set. Like I have a set of a permutation of the items and I combine all possible ways. I have permutations that permute items and permute bidders. But it shouldn't be. It doesn't have to be a product set. Okay. So
it's the same permutation acting on the bidders and the items?
No. It could be So every point in S specifies how to permute the items and how to permute the bidders. And it could be different permutations, and it does not have to be a product set. And the result is general. It does not apply only to the settings I consider, but its algorithmic implications are useful in the settings that are considered. Notes. This result is obviously, it's obviously not going to go through for deterministic auctions, so I have to do randomized auctions to get away to using this result. So there are settings where the optimal deterministic auction does not have the is not going to respect the symmetries of S. And in the settings I consider, because this set is going to be rich enough, it's going to certify the existence of a succinct solution to my problem, except it does not necessarily show how to find the solution. Right? So I have this giant LP. This theorem in the settings that I consider is going to certify the existence of a succinct solution, but it's not going to give me a way to compute this solution. All right? So let's see what it gives me in the settings I consider. So going back to my linear program, now here I can only consider equivalence classes under the subgroup of permutations of bit vectors. Okay, so for the settings that I consider, my variables, my necessary variables go down. Okay, I can only use a representative from every equivalence class of my permutations. Unfortunately, though, I have a problem with my incentive constraints, because still, even though I can represent all the original variables as functions of my representatives, here my deviations can still be exponentially many when I write down the truthfulness constraints for one representative. He can still deviate to many other possible bit vectors. So that's where the symmetries get me. Okay, so they certify that there is a succinct description, because it just express everything in terms of representatives, but they don't give me a way to find the solution. Okay, so that's where we need the second idea, and that's monotonicity. All right, so just to remind you, if you've ever seen the proof of Myerson, monotonicity is very important in Myerson's paper. It is a way to reduce this huge solution space to a small solution space. Okay, so that's a workhorse, really, the proof. What does monotonicity say in Myerson? So if a single item mechanism is truthful, then it has to be monotone. It has to have a monotone allocation rule. In Bayesian incentive compatibility context, this says that for every bidder, in expectation of everybody else's bids, assuming they bid truthfully, the higher the bidder bids, the more likely it is that he gets the item. Right? That's what monotonicity means for Myerson. And really, a lot of the trouble of extending Myerson's result to the multidimensional settings is that we don't have a good, useful monotonicity property. We have notions of monotonicity satisfied in multidimensional domains, except they're not algorithmically useful. All right? So the surprising thing is that once you have symmetry, you get back monotonicity. And that's the next realization that we made. All right? So the proposition, the proof is really simple. So if a multi-item mechanism is both truthful and item symmetric, then it is monotone. All right? And item symmetry here is crucial. Otherwise, you have to deal with more complicated, weak monotonicity in certain.
Symmetric meant which of the two, the left to the right case, which was the thing. So
item symmetric means that that I can say permute the names of the items, and the value distribution is not going to change. Okay. And in our context, this says that for every bidder I, if she bids higher on item J than item K, if she gives a bigger bid to item J than item K, then in expectation of everybody else, he's going to get the item J with higher probability than the item K. Okay, that's not true outside of the setting. Okay, so it only works because of item symmetry. Because it could be that so there are these examples where this naturally looking definition is not satisfied outside of this setting. Yeah.
You don't have anything to say about stronger IC here, like dominant strategy?
Yes, so there is an equivalent. There is yes. So, but it's going to be slightly more complicated. So okay. Basically, it says that if everybody else is indifferent about these two items, and you bid higher on one than the other, you get that with higher probability than the other.
Do you have anything to say about deterministic rules or only randomized?
No, for randomized. Yeah, yeah, I'm using symmetry. I mean, wait. So I mean, if you're looking at a mechanism that's item symmetric, I believe that you get back this type of orthonicity. Okay, so.
So you're really a thing with a claim that that's without loss, but if I'm willing to insist on it.
Yeah, yeah.
Okay.
Yeah, if you're willing to insist on it, you might lose revenue, but you're going to get monotonicity back at least.
But you're using additivity crucially here, I see.
Yes, I'm using additivity. I mean, I believe that this result would go through if your valuation function was anonymous, item anonymous.
Yeah.
So the theorem now, right, and then, as a result of that realization, if you have both monotonicity and a rich group of symmetries, subgroup of symmetries, then you can actually make the LP succinct, right?
So wait, the proposition was only for item symmetries.
Yeah.
There would have been an analogous one for when the bidders were symmetric?
So if the bidders is symmetric, I don't need it.
It's even easier somehow.
Yeah, so the LP is already succinct. All right. So the only reason the LP may fail is if I have many items.
So if you have monotonicity, you can reduce the number of constraints to polynomial, right? And suppose I say your auction is monotonic, the fitting distribution of valuation.
I cannot make, if it's not item symmetric, I cannot express it in terms of representatives. So in principle, it could be monotone, but different profiles of bids, I still need to keep track of different allocation functions for different bid vectors. So the incentive, the deviations, I can restrict them to a small number. The deviation part of the linear program can be made small. Nevertheless, the number of variables still remains large.
But can't you look at the dual? A dual would have exponentially many constraints, and then you try to write an ellipsoid, try to find an oracle.
Maybe. Right, so exponentially many variables, but a small number of constraints, yeah, maybe. I haven't done it because I didn't have a guarantee that's going to be optimal. But you can try to do that. You can say, I want to find a monotone allocation rule. So, all right. So let's. So the next idea is going from continuous to discrete distributions, and that's is going to use the idea of surrogate bidders. And let me recap where we stand. So far, I have optimal Bayesian incentive comparable, or IC mechanisms, if the support of every marginal of the value distribution is of constant size and discrete, and if the value distribution has a rich enough subgroup of symmetry. So this is where we stand. Okay, I cannot do continuous or infinite support distributions yet. And I have to find a way to do that. So how do I deal with continuous distributions first? So suppose my distribution is in 0, 1, finite, 0, 1, but continuous. How do I use the previous idea to get a mechanism? So the trivial natural idea is to discretize D to a distribution D prime that basically samples D and then rounds everything down to the closest multiple of epsilon or power of 1 plus epsilon, doesn't matter. So that's a natural idea. The question is, how much do what does that do in my incentives, in my revenue, or whatever? Okay. The point being that for a discretized distribution that arises by this coupling, I can use my linear program to get a mechanism. So now it's easy to see that M prime is already epsilon IC and epsilon big for the original distribution. Okay, so that's the continuous, and that's a discretized. So I turned the continuous to a discretized. I used the previous approach to compute an optimal mechanism for the discretized distribution, and that already is, you can show it is an epsilon IC or epsilon big mechanism for the original distribution. And that's where we stop for IC. We cannot fix this, we cannot remove this epsilon from the incentive constraints. However, we have a fix for making this truly big, truly Bayesian incentive compatible. By the way, epsilon IC and epsilon big means that I have an at most epsilon incentive to misreport my bid. And what I want to do is I want to turn this to truly big, meaning that I have no.
So incentive meaning I might, if I change my value, I gain by at most epsilon.
Yeah. All right, so for that, I'm going to use a construction that's inspired by a paper of Hartline, Klanberg, and Malekian. And I believe Bobby presented this paper here at some point in the past. So its application here is not, so it doesn't work by itself, but we are inspired by that, okay? So, and I'm going to draw some connections while I describe it. So here's how it works. I have 10 minutes? Okay, yes. I think I can finish with some part of the talk. So here's the main idea. So I'm going to create a meta game for bidders to play. So in this meta game, the bidders that are sampled from the continuous distribution are going to purchase discretized surrogates of themselves. Okay, so a bidder with some value vector for the items is going to, during that meta game, purchase a discretized bidder sampled from the discretized distribution. And then what I'm going to do is I'm going to have the surrogates that they purchased in the first phase play against each other in the mechanism that I computed for the discretized distribution. All right, so more details. So the meta game is as follows. So I'm going to set up, so every bidder is going to play a meta game by himself against replicas of himself. Okay, so they're not, the bidders in the first phase where they purchase the surrogates are not going to interact with each other. They're going to interact only indirectly. But in the first phase of the metagame where bidders are supposed to buy surrogate bidders, they're going to play against replicas of themselves. All right, so every bidder I is going to play a VCG VCG auction against make-believe replicas of himself, and these replicas are sampled from the continuous distribution. All right. Now, the goods for sale in this VCG auction are going to be surrogates, that is, discretized bidders that are sampled from the discretized distribution. And di and di prime denote the marginal of the big distribution over one particular bidder. Okay, so what I'm going to do is I'm going to sample many replicas of bidder I from the continuous distribution, and I'm going to sample many surrogates from the discretized distribution, marginalized on that particular bidder. I'm going to set up a VCG auction where the goods for sale are the surrogates, and the bidders are the replicas and the bidder. And the value of a surrogate vi prime for a bidder vi is the utility that of vi for the outcome that vi prime was gonna have if he played in the mechanism m prime against discretized opponents. Okay, so the value of surrogate vi prime, which is a discretized thing, to bidder vi is whatever utility vi would have for if vi prime was going to play in a mechanism m prime against discretized surrogates.
Is there any relationship between the I games and the J games? I mean, so is each bidder playing an independent game?
Yes.
At this stage, so in this first stage, it's
so it's really, I mean, there's really no second stage. It's mental in some sense. Okay, so I have to check some consistency, but in some sense, every bidder is going to play an independent VCG game, and the way I'm going to set it up, there is going to be some, whatever they're going to pay is what I want, and I will have a way to implement the outcome that I promised them in their individual VCG games. Okay, so if VI buys a surrogate VI prime, I have promised him some probabilistic allocation rule and some price. Right? So I set up these independent games. If there's no way from me, after they buy their surrogates, to implement what I promised them, then I'm in bad shape. Okay, so I have to set up independent auctions where people buy surrogates in a way that whatever the outcome of these VCG auctions are, there is still room for me to implement the allocation rule that I promised.
I see. So the utility VI of the surrogate VI prime depends on all the other valuation.
It depends on what surrogates the other guys buy.
Right, and in turn,
and
on their values.
Yeah. Okay, so unfortunately I don't have time to give the precise details, but at least at an intuitive level, this is what I'm going to do. And you know, I'm gonna, you know, like the computation that goes into computing the VCG auction is easy. So it's just a Maxwell matching. Okay, so there are many issues that arise with this construction. So let me just, you know, go through the issues and give you some intuition about what may go wrong. So consistency. Why whatever I have in mind doing is not gonna get something bizarre. Okay, so I'm setting all these independent VCG auctions. Why is it, you know, I'm never gonna be in a position where I have promised to give the painting to both bidder I with probability 1 and to bidder I prime with probability 1. So if I'm in that shape, I'm screwed, okay? All right, so I have to make sure that I'm never in a position where I have promised too much, more than I can do, okay? So, or another thing that may go wrong is if the bidder I doesn't buy anything in the VCG auction because he doesn't find any surrogate that he likes. Right? So all surrogates may possibly give him, you know, negative utility. So he's not going to buy any. So if he doesn't buy any, then the number of surrogates that are going to participate in the latter mechanism, that's mental, but still is there, are going to be fewer than expected. So that's going to make the scheme invalid because whatever I promised to the other people is off from what it should be in expectation, right? Because this guy didn't buy anything. So the competition in the latter mechanism is smaller, so they're going to get different utilities from participating in that mechanism. So the easy fix that, the easy fix for that is just, you know, like in the case that bidder I didn't purchase any surrogate, I'm just going to give him a random surrogate that is left over in this VCG auction. I'm not going to charge him anything for that, so he doesn't care. But I'm also not going to give him any utility if the surrogate succeeds to get some utility out of the mechanism M prime. So that's fine as far as the consistency goes, except that it may screw my revenue. So that's something I'll have to deal with later. Okay, but keep it in mind. So that's why I put it in orange, assuming you're following what I'm talking about. Efficiency. So the surrogates are gonna play the mechanism prime, and really my revenue is going to come from the mechanism prime. I'm not going to care about what VCG revenue is, and for the revenue from M prime to be reasonable, close to the optimal, I need the number of replicas to be proportional to the support of the marginal distribution, and that's exponential as we've seen. So I'm still in bad shape because my VCG auction needs to be huge if I have many items. It turns out that this is not an issue because I can still use monotonicity and make this go through by using representatives of value vectors. So that's not really an issue. I'm just mentioning that. So let's go to the revenue, which is a real issue. So what I hope from this scenario is I hope to get as least as much revenue as M prime gets. Okay, because in principle, the surrogates are going to play M prime, right? And whoever purchased the surrogate is going to pay for his price. So So I'm hoping to get as much revenue as m prime. All right? But this contradicts my easy fix here, that potentially I'm not going to charge, I'm going to assign a surrogate to people, and I'm not going to charge him for them. I'm not going to charge these people for the surrogate they got, because they had negative utility in the VCG matching, so I cannot, these guys are not going to pay anything for what the surrogate does in mechanism M prime. So on the other hand, if this was not happening, the reason for my optimism is that because I sampled the surrogates in the VCG auctions from di prime, really, as far as m prime is concerned, the bidders come from the discretized distribution. So if this phenomenon wouldn't arise, then the profiles that are participating in m prime are really coming from the discretized distribution for which I designed my auction. Right? So if there was not for that a thing, then I would get the revenue I want. Okay, so, but the problem again is if a VCG mechanism, some VCG mechanism gives some surrogate to somebody for free. In that case, he's not going to pay for anything. And the idea for fixing that is I'm going to make surrogates a bit cheaper, and one can play with matchings and show that this issue is not an issue. But that takes some technical work, and I'm not going to get into that. All right? So just to conclude this very schematic exhibition of the proof, why is it truthful? Obviously because every bidder just participates in a VCG auction, and VCG auctions are exactly truthful, so there's no epsilon lost in the incentives here. Okay, so that's the idea. The idea is that you plug in a front end to every bidder. So every bidder was epsilon truthful. If he were just to play m prime, what we do here is we put a front end for every bidder, and that front end is a VCG auction, so he's going to play truthfully. All right, and really what we do is we transfer some loss from the incentives to the revenue. So the epsilon in the incentives gets transformed via this reduction to the revenue. Okay? So it's a truly Bayesian incentive comparable mechanism, but the revenue is a bit smaller. And that's the high level idea. All right? So that was meant to be schematic, but this is a
epsilon either in the incentive compatibility or in the optimality?
Yes.
Okay.
So far, okay, so what do we stand? So we know everything for where the marginals are constant size, and we have the rich set of symmetries that I described. We also know if the distributions are continuous but they're bounded in a set, what happens if my distributions are a Gaussian or an exponential or some other distribution that has infinite support? How am I going to deal with this situation? All right, so, and for that, we need a different approach that's probabilistic. And it goes in the form of developing extreme value theorems for distributions that we're interested in. So let me just show what happens here. So extreme value theorems, all right? So recapping. So far, O minus epsilon, when the distributions are normalized in 0, 1, can I do a factor of 1 minus epsilon instead, if my distributions are not bounded, are not finite? So here is an example theorem that we have to establish to make this possible. Okay, and that's with Yang Kai. So suppose x1 through xn are independent, but not necessarily identically distributed random variables that are monotone hazard rate. Recall that this could be Gaussian, exponential, uniform, whatever you want. Okay, but it has to satisfy the monotone hazard rate condition. So here are the distributions. All right, so they fall, fall all over the place. This is the infinite line. They can fall in all sorts of places. They do not have to be identical. So here's a surprising result that we show about the maximum of these independent random variables. So we show that there is an anchoring point beta, okay, falling somewhere in the line, with the following properties. If I look at the max of these guys, the max falls to the right of that point with at least some constant probability. All right, that's okay. So I can do that for every variable, whatever. Okay. But the crucial thing is that if I shoot off 1 over epsilon times this guy, if I shoot off to 1 over epsilon times beta, then the contribution of whatever samples of the maximum fall here to the expectation of the maximum is tiny. So the contribution to the expectation of the maximum from all samples of max xi that fall to the right of this point are small, are at most epsilon times beta.
So these MHR random variables are always supported on 0 to infinity?
No, they could be bounded, but the more interesting case is when they're all over the place. Yes, they're not negative. Yeah. All right. So let me repeat. So because the probability of max xi to the right of this is at least a constant, then the expectation of this guy is at least beta, some constant fraction of beta. But what could happen is that the expectation of the maximum has a lot of contribution for values that are higher and higher, that are high and very far from this anchoring point. What this guy says is that, nevertheless, if I shoot off 1 over epsilon times beta, there's no real contribution, interesting contribution to the maximum coming from these sides. So in other words, what this says is that if these were the values of the bidders for the items, most of my revenue comes from a bounded set, from a set that is epsilon times my anchoring point up to 1 over epsilon times my anchoring point. So there's what it says that like if I have a maximum of random variables that are all over the place, there is a bounded set that is a function of this anchoring point, but the ratios of the lower and the upper bound is just constant factor, it's a function of epsilon. So that all the expectation of the maximum just comes from samples falling in that set. Okay, so that's very surprising. Okay, so
if I just defined the random variable x, which was the maximum of x1 to xn, and applied Markovs to it, what do I get? I mean, won't I get the same thing?
No, you're not. So, and you have to think about it. So what Markov is going to tell me is that the probability you fall to the right of that is small. But it could be that you get a huge contribution to the expectation from that point. All right, so that's not Markov's.
So Markov always says that the expectation everywhere is a constant.
That the probability to the right of if I shoot off a constant factor, any constant factor of my expectation, the probability I fall to the right of that is small. But it does not imply that the contribution of these points to the expectation are small. It could be that I get, like, a huge number with probability, 1%. Still, that contributes a lot to the expectation. So what this does is goes beyond that. Yeah, but that's a good point to get intuition.
And n, what role did n?
N does not, that's surprising, n does not come into play.
For every n?
Yes, that's true for every n. But you might ask, what the heck, right? So beta is going to be a function of these random variables. Right? So beta is a function of the distributions of these guys, but if you compute it, then you know that your expectation falls in a bounded set in some sense. So the ratio of this guy and that guy are just a function of epsilon. So whatever epsilon you want, I can give you so the same beta for every epsilon you want. I know that if you tune your window around this beta in this way, then you have this guarantee.
But if n equals 1, then this is something that's not true for general random variables.
That's true.
This is something that's implied by the MHR condition, whatever that is.
Yes.
I see.
That's
Okay.
right. Right. For a Gaussian, for instance, it says that, right, so if I go around the mean, I get most of the expectation for a Gaussian. Okay, so I guess in some sense, yeah, so it shows, this concentration result for the Gaussian, but it shows a concentration result for maxima of independent random variables.
What this MHR means, like just roughly?
Yes, if I had a board, I would. So it means that if I look at any point, does it open, this thing?
Yeah, the middle one does, but then you'll be writing behind the screen. So let's not consider. That's not exactly a whiteboard.
Okay, so basically what it says is that if I look at any point in the support,
Okay.
and I look at the probability on that point, sorry, if I look at the ratio of the probability of that point to the probability to the right of that point, that's an increasing function. So the ratio of the probability value at some point over the 1 minus the cumulative at the point is called the risk of the distribution. And you want it the hazard rate, and you want it to be an increasing function. And you can check that the Gaussian, as you go to the right, the significance of that probability compared to the tail gets larger and larger. Right? Makes sense?
Yeah, I mean, what it's saying is that right, the tails are thinner than the tails of an exponential distribution. That's in some ways what this thing is saying, is that the upper tails of those distributions are always small in this sense.
I mean, yeah, so another thing it says is that if I take the log of 1 minus the cumulative, that's a concave function, if that's useful. If I get 1 minus capital F of x, I take the log of that, that's concave. The derivative is exactly, yeah, I don't know. Is that?
I like Glenn's explanation.
Yeah, okay.
So the reason you get this tight concentration is because you don't have a lump in the future.
What?
So you don't. The reason that you get a tight concentration beyond your mean of the max is that because the MHR implies you do not get a lump somewhere in the future. Because in that way you could have very large concentration.
A lump center, yeah.
Okay. So some kind of smooth tail will give you.
It really means, yeah, so it means that my tails are not, parallel distributions are not Monotone Hazard Rate, okay? And in fact, with Young, we show an analog of this theorem for regular distributions that include Monotone Hazard Rate, but also include power laws. And over there, it's much harder to first obtain the extreme value theorem, and also it's weaker. So it says that, what it says is that the balance of maximum over minimum is a polynomial in n rather than an exponential in n. Okay, so still, I mean, in principle, where the contribution goes could be an exponential size set. What we show is that for Monotone Hazard Rate, it's a bounded set. For regular distributions, a polynomial set. Yeah, so I'm almost done basically. So just to do an overview of the proof again. So we start with a value distribution that has a rich subgroup of symmetries. We show that the optimal auctions have to satisfy the same set of symmetries. Using the symmetrization, we also have the monotonicity of optimal auctions. And this way, we can set up a discretized LP with the same set of symmetries, and we can solve it succinctly. Right? So that's one group of ideas. The other idea is going from bidders to surrogate bidders. Right? And the third idea is to use to prove extreme value theorems for the types of distributions that we are interested in. So putting all this together, we get the optimal auction for a distribution with a rich set of symmetries. All right, so that's it. And just to provide a summary of the main results, just for you to remember what we have is constant number of items or constant number of bidders. In this case, a bidder can have an arbitrarily joint distribution over the items, but bidders have to come from the same population. In the other case, every bidder has to have i.i.d values for the items, but people can use different distributions. So I had two possible endings for this talk, because I didn't know if I could go talk beyond symmetries, so forget about that. So let me go to my second ending, the pessimistic ending. Open problems. Okay, so what is the complexity? I can do opt minus epsilon or 1 minus epsilon times opt. What is the complexity of the exact problem? Can I pin down exactly the optimum? I think not, and I believe it's a Sharpie complete problem, but I cannot show it. All right, so I believe that even if you have a single guy interested in many items and you want to hit opt exactly, you have to solve a Sharpie complete problem. But I mean, if that conjecture is true, it really shows that like the interaction between computer scientists and economists is a useful one, because approximation is really in the business of computer scientists, So somehow such a result would motivate why we have to look at approximations. That there are problems if you want to provide a closed form solution of these things. So how about going beyond the rich symmetries that are used in this framework? So we can do it. So that's the result I would have presented, but I didn't. But maybe that's better because we went over the other things more slowly. So beyond additive symmetric settings, we can do that for a single unit demand bidder interested in buying many items, but with potentially non-i.i.d distributions for these items. Okay, so if this single unit demand bidder had i.i.d values for the items, we can use my result with MAT. What I presented today, we can solve it. Okay, because it's going to be an additive symmetric auction because of the symmetries in the items. But what happens if you have a non-i.i.d bidder? So we can solve that case with Young. And that requires the extreme value theorems for Monotone Hazard Rate or regular distributions that I talked about today, but also some interesting algorithmic component. And finally, are there simple mechanisms for doing this stuff I presented today? So the auctions I presented come from an LP. I have some structural understanding of how the solution looks like. It has to be symmetric. It has to be monotone. It has the form that I presented today. But is there a simple mechanism like the eBay auction that gets close to the optimal revenue? For instance, the challenge problem I presented earlier. eBay with 2 items, everything i.i.d. Is there a simple form of the optimal auction? All right. So if there was a single item, I said before that a remarkable coincidence is that there is a deterministic truthful auction due to Myerson. Is that a singularity, or can I extend that to, say, 2 items? All right? Or is there no succinct description of an optimal auction in this setting? All right? So with these problems, thanks a lot for listening.